Okay, so let me begin by starting with a summary of what we were doing last time. And I think it's better if we start with you. So Zain, आप थे last class में? So can you give a little bit of summary of what we did last time? जो environment है?
Environment को minus trace out करके
Mhm.
फिर system का evolution जो था projection
Mhm.
इस तरह से
So this is funny because what I had in my mind, what we did is completely different from what we have said. But what you have said makes total sense. क्यों? क्योंकि आपका जो quiz to find out what operations happen to that smaller part of the bigger system by tracing out the environment. और आपको याद वही चीज है. But essentially, what we were trying to do, what I think I was trying to do, because that was just a minor side thing. But what we were trying to do is come up with a way of describing quantum operations that can give to non-unitary evolution. So our goal, which includes the noisy system as well, that we started discussing quantum operations, or you can say evolution of quantum system. But this time, our quantum system may not be in a pure state. Our goal is that we have a system in a potentially a mixed state, and then we have a process which may not be a unitary evolution of this system, and we obtain something, let's call it the uh, the map. So this process has several names and they're all mean the same. So these are the things that I will be using for this. It's, you can call it map, you can call it quantum operation, or we can call it channel. This is, by the way, the more frequently used word. Or we can also call it quantum process, or we can sometimes call it noisy evolution, or we can just call it evolution. So essentially anything that is happening to this quantum system, any physical thing, okay, let me not just say anything that you can come up on paper, but any physical thing, उसके लिए हम जो है वो we were trying to develop a mechanism. And since the things that are being done to this are done by the environment, so we had environment last time as well, but essentially we want to understand the behavior of this quantum system under these physical quantum processes. That's what we were trying to do. And for this, we had come up with, and we actually said that there are three ways that we can describe the quantum operations. One was the differential equation, way that we have saved for the end. This is essentially thinking about the system and environment, as one quantum system, and then evolving the whole quantum system unitarily using Schrodinger equation, and from that equation for the system and environment, just trying to find the equation only for the system under study. That equation is called master equation. We will get to that formalism later on. But the next one that we started was what we call this operator sum method. And this actually was like this, that if we have a state rho, we can express its evolution using quantum operations like this, where these EIs are any general operators. The only condition they have to satisfy is this. That the processes are complete. That this defines everything that can happen to the system is contained in this, because this is equal to identity. So all possibilities are included. And this operator sum method, we obtained this one, if you recall, from by tracing out the environment, because we said that if we have, our system and we have the environment and they are, interacting with each other. So this is a closed quantum system now. So if our environment starts in some state and we have our system start in some state, and these quantum operations or this quantum map for the system only, we can get it by tracing out the environment from the, because this is, the system environment. They are now, since it's a closed quantum system, they are evolving unitarily. So this U dagger will evolve this unitarily, and then from this we can trace out the environment. So we were working out this, these operations from this total unitary operation by tracing out the environment, and that's what Zan meant when he said that, right? That we were trying to see what happens to the system if we take out the environment. Anything else that we did last time? So if we have a closed quantum system, then this map for closed system, this map is simply a unitary evolution like this. Okay, and for open system, this map is non-unitary like this. We have more than one operator, and no, we don't require these operators to be individually unitary, but we require this product to add to this identity. Because for this, we only, for the closed system, we require this, right? U dagger has to be identity. There is similarity, but there's more to this thing. By the way, these, can be constructed from unitary operators. We will see shortly, and we also saw in an example last time. So let me, give a summary. Our total system, which includes the principal system and the environment, evolves unitarily. But we almost never have access to the environment, or at least not a complete knowledge of environment. So most of the time we are restricted toward only with the principal system, which is just a part of a bigger system. And we, if we want to see what happens to this system under different, noise processes, the one method is the master equation method that we will briefly touch later on. But this method that we introduce, operator sum method, this we can get by tracing out the environment from the total, system. The trouble with this thing is this, that these individual EIs, they are found by this thing, by, projecting this unitary operator onto the eigenbasis of environment and tracing out only the environment part. If we want to follow this route, there's a big trouble. We need to have a complete knowledge of environments, right? या और जैसे लास्ट एग्जांपल में आपने देखा, मैंने आपको बता दिया था कि सिस्टम इन्वायरमेंट इंटरेक्शन क्या है, कंट्रोल नॉट गेट था. We took one example. फिर दूसरे एग्जांपल में I just gave you explicit unitary operator, ये जो U है, which was specifying the interaction of the system with the environment. But that we rarely do. So there is an alternative way of, coming up with a description of this quantum process, and this is called axiomatic approach. And this is what we are going to discuss today. And then I'm going to show that this is equivalent to this. And later on, we will see that this is just sort of a special case of this. So what we are studying here is actually general, even more general than, little bit more general than master equation approach. Okay, so this axiomatic approach starts with specifying the quantum channel only by talking about the system and specifying its properties so that it corresponds to physically sensible things. So this time we are not going to come to the operators by tracing out the environment, but let's forget all of this for a moment and start totally fresh. So we have a quantum process which is specified by this channel E of rho. And let's see, for this to be physical, what properties does this map has to satisfy? Number one property is that it should be trace preserving. Trace preserving mean the trace of this map should be equal to 1. Excluding measurement, by the way. If we include measurements, also constituting a quantum channel or a quantum process, which in general it is, then we can say that the trace can be less than 1. But if we exclude measurement, treat measurement separately, then we have to make sure that whatever process we have, our trace is going to 1. And why this is a requirement that we need to have for this map? And can you guess? Let's say Ali Raza. Ji? You can, okay, you see. हाँ लेकिन क्यों देखें, ये जो मैप है इसके बाद you still have a density operator. So basically what we want to put conditions on this map is only to make sure that our density operator, valid density operator, maps to a valid density operator. That's all we want. क्योंकि अगर आउटपुट भी वैलिड डेंसिटी ऑपरेटर है तो इसका मतलब है कि आउटपुट फिजिकली सेंसिबल है, तो जो भी प्रोसेस हुआ है दिस कैन आल्सो बी फिजिकली सेंसिबल. और जो डेंसिटी ऑपरेटर्स हैं, इफ यू रिकॉल, उनका जो हमने उनको जब डिफाइन किया था, वी सेड दैट दीज आर ऑपरेटर्स व्हिच हैव ट्रेस्ड वन, and the traced one was there to make sure that sum of all probabilities is equal to 1, all measurement probabilities. Okay, so that's why our whatever our map is, this map has to satisfy this trace preserving property, which is just to make sure that our output is a valid density operator. Second property is that it should be linear. And actually there's a little bit confusing term used for this. It's called convex linear. So our map should be convex linear, which simply means that if I have P1 row 1, P2 row 2 goes into this map, at the output I should be getting P1 E of row 1 plus P2 E of row 2. Okay, and this is called convex simply because this is not a general linear requirement. The general linear requirement is that, let's say these P1, P2 can be negative, positive. But here, since these have to represent probabilities, we only require it to be convex linear, that for these positive coefficients, our map should map to this, these positive number P1, P2. But, forgetting this technical thing on the side, we just require this map to be linear. And let's see why this requirement is there. And जी नहीं उसमें तो करते हैं, but why here? It's a general quantum operation. So why this linearity is being demanded from this physical process? ओके सो इसको आप समझ सकते हैं इस तरह से कि जो हमारी इनपुट है, जो डेंसिटी ऑपरेटर itself, by the way, when I write a density operator, what does it really mean? It's an ensemble. ensemble का मतलब ये है कि अगर एक ओवन है जहां से आप कोई किसी चीज की स्टेट्स प्रिपेयर करके भेज रहे हैं, so there are two meanings to that. So one is that, and they're both equivalent, that you're sending, let's say, one particle at a time, और आप चूज कर लेते हैं कि आइदर पार्टिकल की पोलराइजेशन इसके अलोंग है या लेट्स से परपेंडिकुलर डायरेक्शन में. So it's either this or this or this or that. So there is somebody here who is deciding कि आपने ये पोलराइजेशन अटैच करनी है, ये करनी है. And suppose there are some probabilities, आप कहते हैं कि 30% probability के साथ ये कर रहे हैं, 70% probability के साथ ये कर रहे हैं. Okay, so your density operator is essentially, let's say, this represent to this zero state, and this probability P1 represent to this one state. अब देखें, और दूसरी इंटरप्रिटेशन पे हम आते हैं. अब यहां पे कोई फिजिकल प्रोसेस है, तो अगर ये कुछ प्रोसेसिंग कुछ करता है इसके साथ, लेट्स से कोई फोटॉन्स के साथ स्कैटर होते हैं, अगर ये मैसिव पार्टिकल है, या कोई भी जो नॉइजी प्रोसेस है, अगर ये एटम्स आ रहे हैं, लेट्स से आपका एटम है कि वो कुछ एक्साइटेड स्टेट में आ रहे हैं, कुछ जो है वो ग्राउंड स्टेट में आ रहे हैं. सो देयर माइट बी सम रेडिएशन फील्ड प्रेजेंट हियर, कि अगर ये एक्साइटेड स्टेट में आ रहे हैं तो दिस रेडिएशन फील्ड माइट बी डी एक्साइटिंग देम, as happens in laser. Yeah, this might be exciting them. So whatever something is happening, so we should imagine that whatever our description is, it should be like this, कि अगर ये जीरो स्टेट आ रही है तो इस पे जो कुछ भी ये करता है, और या अगर ये वन स्टेट आ रही है तो ये चैनल इसको कुछ करता है. ठीक है, सो वी शुड बी रिक्वायरिंग के अगर लेट्स से कुछ पार्टिकल जीरो के साथ और कुछ वन स्टेट के साथ आ रहे हैं, इट्स मीन दैट देयर इज दिस प्रोबेबिलिटी डिस्ट्रीब्यूशन और दिस डेंसिटी ऑपरेटर. वी इट्स नेचुरल टू एक्सपेक्ट कि जो आउटपुट पे पॉसिबिलिटीज है डेंसिटी मैट्रिक्स की, वो या ये है या ये है, विद द सेम प्रोबेबिलिटीज. कि अगर इनपुट पे जीरो गया है तो हमें आउटपुट पे जीरो को कुछ हुआ मिलना चाहिए ना. अगर इनपुट पे वन गया है तो वन को, इसका मतलब है कि जो प्रोबेबिलिटी जीरो और वन की है, जो आउटपुट पे है वो उन्हीं प्रोबेबिलिटी के साथ हमें उन स्टेट्स को जो हो रहा है वो मिलना चाहिए. सो दिस लिनियरिटी is also a physical requirement for this matter. And there is a third requirement, and this is actually a little bit tricky initially to understand, which is stated as complete positivity. Okay, so let's first understand the requirement for positivity. Positivity की requirement is coming from the density operators. Okay, density operator, if you remember, we have defined them to be operators which are positive, which means that their eigenvalues are positive. Or you can say कि अगर आप इनको किसी भी state में इनकी expectation value find करें, you get a positive number greater than zero. Okay, so which also makes sense कि अगर आप इसको p row को diagonalize करते हैं, you have these probabilities on the diagonal, so all those numbers have to be positive. So requirement of positivity comes from our insistence कि input पे अगर density matrix जा रहा है तो output पे भी valid density matrix होना चाहिए. But this complete positivity is little bit more than just positivity. So this actually means कि अगर आपके पास एक complicated system है, let's say your system consists of 3 atoms going into whatever this quantum operation is. So एक atom है, 2 atom है, 3 atoms are going into this thing. And you can write a density operator corresponding to the joint state of all of these atoms. Now suppose that whatever this quantum system, quantum operation is doing to your system, let's say it only does it to one atom and it doesn't do anything to these. हो सकता है कि ये वैसे इधर से ही गुजरते हैं. Suppose, so पहली बात है कि देखेंगे ये physically एक realizable चीज. It's not something which is physically not possible. We can have our operation mechanism only impact part of the system and not the rest. But whatever we do, we still get a physical state over here. So it means our map should be such that we should still get a valid density operator, whether the map is applied to only part of the system or the total system. This is what we call complete positivity. Let me give you an example. So trace operation. So let's say this is a mechanism, this is a quantum system which takes trace, this is not the trace, transpose. Trace is actually a valid quantum operation. Transpose operation. So this is, suppose there's an imaginary physical quantum system which takes the transpose of the input state. अब अगर let's say rho जा रही है input, तो output में हमें क्या मिलेगा? Rho transpose. And we can very easily show कि अगर rho valid है, तो rho transpose भी valid होगी. So it means this transpose is a positive map if it is applied to all of the rho. Albatta, let's see by an example that if we only take partial transpose, we take transpose only a part of the system and not the whole system, then the output state is not a valid density operator. And let's do it by example. For example, let me take Bell state. Let's say we have two particles prepared in a Bell state. Suppose that Bell state is, let me take this 0, 0, 1, 1. So this is the state of this, these two particles which is going in. And suppose the system only applies the trace, the transpose operation to this qubit A and does nothing to this qubit B. And let's see कि input density operator क्या है और जो output density operator है वो क्या है. Okay, so input density operator I can easily get. इसको लिखा. Okay, so and this is by the way 0, 0. इसको यूं लिख लेते हैं, आसानी देगी. और इसको अगर मैं मैट्रिक्स फॉर्म में लिखूं तो ये डेंसिटी ऑपरेटर बनेगा 0, 0 स्टेट ये है, 1, 1 ये है, ये भी 0, ये भी 0, ये 0, 0, 1, 1, ये 1, 1, 0, 0 है. सो ये इनपुट डेंसिटी ऑपरेटर, ठीक है, मैट्रिक्स की फॉर्म में लिख लें या यू ऑपरेटर की फॉर्म में लिख लें. परफेक्ट. अब जो है आई वांट टू डू अ पार्शियल ट्रांसपोज ओनली ऑन क्यूबिट ए. सो क्यूबिट ए की पोजीशन, रिमेंबर द फर्स्ट वन इज क्यूबिट ए. सपोज अब देखिए हमने ट्रांसपोज कैसे लेना. ठीक है, ट्रांसपोज के लिए let me do the transpose here, partial transpose. So rho पार्शियल ट्रांसपोज अनक्यूबिटेड। ट्रांसपोज का मतलब है अगर आपके पास कोई ये मैट्रिक्स है तो इसका ट्रांसपोज आ जाएगा ए डी सी बी, यानी ये बी अगर कोफिशिएंट है 0 1 स्टेट का और सी अगर कोफिशिएंट है 1 0 स्टेट का, तो ये बी और सी जो है वो इंटरचेंज हो गए। दूसरे लफ्जों में दिस 0 goes to 1 and 1 goes to 0। ठीक है, इनको आपने इंटरचेंज करना है। अब यहां पे देखें, ये जो स्टेट है ये क्यूबिट 0 ए की है, ये क्यूबिट ए की है, ये बी की है, ये बी की है। तो इसका मैं ट्रांसपोज लूंगा तो ये 0 और 0 इंटरचेंज हो जाएंगे। सो आई विल गेट हाफ 0 0 0 0। इसका लूंगा तो ये 0 और 1 इंटरचेंज हो जाएंगे। तो ये आ जाएगा 1 0 0 1। इनका ट्रांसपोज लूंगा तो ये 1 0 इंटरचेंज हो जाएंगे। 0 1 1 0 और ये 1 और 1 रिप्लेस होंगे तो आई स्टिल हैव द सेम थिंग। अब ये मेरे पास स्टेट आ गई। समझ आइए मैंने ट्रांसपोज कैसे लिया उन्हीं कि मैं सिर्फ पार्शियल ट्रांसपोज ले रहा हूं। ठीक है, टोटल ट्रांसपोज लेना तो आप लोगों को आता है, ये मैट्रिक्स इसका ट्रांसपोज फाइंड कर लेंगे। पार्शियल ट्रांसपोज होता है कि आप सिर्फ किसी एक लेट से जो क्यूबिट है उस पर ट्रांसपोज अप्लाई कर रहे हैं। तो ये जो हम स्टेट्स लिखते हैं आपको पता है कि हम एक तरतीब से लिख रहे होते हैं। लेट से कि ये अगर पहली ए क्यूबिट की स्टेट्स हैं, दूसरी बी की हैं एंड सो ऑन। तो अब ये देखें, ये स्टेटस में मैंने ट्रांसपोज लेना, पार्शियल ट्रांसपोज सिर्फ ए का। तो ट्रांसपोज का मतलब है कि आपने जो नॉन डायगोनल असल में जो स्टेट्स हैं उनको इंटरचेंज करना होता है। तो इसका मतलब है ये 0 और ये 0 आपस में इंटरचेंज हो जाएंगे। सो आई स्टिल हैव द सेम स्टेट। ये 0 और 1 इंटरचेंज हो गए तो ये आ जाएगा 1 0, ये आ जाएगा 0 1। सिमिलरली ये 1 और ये 0 इंटरचेंज होंगे तो आ जाएगा 0 1 1 0 और ये 1 1 1 1 वही रहेगा। ये डेंसिटी मैट्रिक्स आ। और इसको अगर आप मैट्रिक्स फॉर्म में लिखें, यहीं पे लिख लेते हैं। सो दिस ट्रांसफॉर्म्स टू द मैप इज नाउ हाफ, ये 0 0 1 1 तो वैसे ही है, सो ये 1 और ये 1 उधर ही है। जी जी। सो बेसिकली ये जो मैट्रिक्स है उस मैट्रिक्स पे ट्रांसफॉर्म हो गया। ये मैंने इधर से लिखे हैं, ये 0 1 1 0 1 0 0 1 के कोफिशिएंट ये बनते हैं। दूसरे लफ्जों में अगर आप तरतीब से देखें तो ये जो है ना एक सब मैट्रिक्स, इस केस में इनका ट्रांसपोज हो गया। बहरहाल इस तरह से करना जो है ना इट्स लिटिल बिट ट्रिकी, क्योंकि अगर बी पे करना होगा तो वो फिर ये दोनों इंटरचेंज होते हैं। सो उसकी बजाय जो सिंपल तरीका है पार्शियल ट्रांसपोज लेने का वो हमेशा यही है कि यू कैन जस्ट राइट इट इन ऑपरेटर फॉर्म, और जो क्यूबिट को भी करना है ए या बी को, उसको आप इंटरचेंज कर लें। अब ये जो मैट्रिक्स है ना रो प्राइम, अगर आप इसकी आइगन वैल्यूज फाइंड करें तो इसकी आइगन वैल्यूज आती हैं हाफ 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 और माइनस हाफ, which mean it's not a positive operator, so it's not a density operator, which mean that this partial transpose was not a valid quantum operation because it transformed a valid quantum state to something that doesn't make sense. So this is what we mean कि जो हमारा मैप जो भी हम स्पेसिफाई करें अपने सिस्टम के लिए, it should be completely positive, that a positive operator should transform to a positive operator not only if your operation is applied to the whole system, but also if your operation is only applied to part of the system. That's the complete positivity requirement. By the way, ये मैंने असल में इस ये पर्टिकुलर एग्जांपल की एक और वजह भी है। अगर आपको दो पार्टिकल का डेंसिटी ऑपरेटर गिवन हो and let's say it's a mixed state, how do you work out if it represents an entangled state or not? And the test that people have developed is this: if you take a partial transpose, of either one or the other qubit, and it's only valid for 2-qubit system. And the result is a density operator which has negative eigenvalues, then it means your state was entangled. क्यों? क्योंकि if I had started with a 2-particle state कि जो entangled नहीं है, तो partial जो transpose है ना, by the way, उस case में still it's a valid thing. It gives a positive density operator. Only for entangled bipartite state, the partial transpose give a density operator with negative eigenvalue. So this is also a test for entanglement for bipartite system. जो bipartite के अलावा tripartite या ऊपर वाले system है, उनमें this is only a sufficient condition, but not necessary condition. You might have entangled state, but still partial transpose might not give you negative eigenvalues. अलबत्ता जो tripartite है उसमें भी अगर आप partial transpose implement करें and you get negative eigenvalues, that also mean that states are entangled. But it's only sufficient, not necessary condition. But for bipartite system, it's also sufficient and necessary condition. So if partial transpose gives you negative eigenvalues, then definitely your starting state was entangled state. So this is an entanglement test as well. All right. So any question so far? Gigi? आपको इंफॉर्मेशन लॉस क्यों नहीं नजर आ रहा? हमने यूनिटरी एवोल्यूशन की तो रिक्वायरमेंट गिरा दी है. ओके वो तो ज़ाहिर है वो इन्फिनिट स्टेट से इधर भी उससे तो पता नहीं चलेगा. बट जो इंफॉर्मेशन लॉस है ना, वो असल में उस वक्त होता है दैट एटलीस्ट क्वांटम मैकेनिकली वी से, इसको हम क्वांटिफाई भी करेंगे बाद में, व्हेन योर प्योर स्टेट स्टार्ट गोइंग इनटू मिक्स स्टेट्स, that's where the information loss comes in, and we'll see that that is something that can happen. और अगर आप सिंगल क्यूबिट ऑपरेशन, and we'll see shortly actually in today's class hopefully, if we start with a state which has a block factor at the block sphere, then we can define many physically realistic operation. After those operations, the block vector is somewhere inside the block ball and not on the surface. And we will also start talking about some physical processes where these operations are coming from, which these are modeling. Okay. अच्छा, अब इस जो टेक्निक है इसमें हम देखें, हमने इन्वायरमेंट का कहीं डिस्कस नहीं किया. It's only the system that we are talking about. Even जो principal system है, even जब when we were talking about complete positivity, we were still talking about the part of the principal system, not in the same sense जो हम जैसे हम पहले बात कर रहे थे कि system is a part of a bigger system plus environment system. Okay, so let's see if this thing is equivalent to the operator sum method, and actually it is. So to prove equivalency, we have to prove two ways. If suppose you are given that a map has to satisfy these three properties, can you reduce the map to operator sum formalism? Okay, and that's the reverse process. And then the forward process is that suppose your map is defined by an operator sum formalism, does that satisfy these three requirements? So I'm only going to prove the forward one. You can check the proof for reverse in the book. Okay, so let's prove this theorem that I will call actually the equivalence of operator sum and the axiomatic approach. So let's start with this thing. Let our map is defined by the operator sum with only one condition, that we have completeness satisfied by these operators. So first property, easy to verify. कि अगर मैं इसका ट्रेस लेता हूं, so इसका ट्रेस जो है वो इसका ट्रेस है, तो आई कैन टेक ये जो ट्रेस है इसका, उसमें फिर आई कैन इंटरचेंज दिस ऑपरेटर, दिस कैन कम हियर, ठीक है. और लेट्स जस्ट सी ट्रेस of E row is trace of some EI row EI dagger, and trace is cyclic, so I can take this matrix here and still get the same trace. But this is identity, so this trace is equal to trace row. So we see that this is a trace preserving map. So operator sum formalism does satisfy the first axiom. So if trace row is 1, trace E row is also 1. Linearity is easy to check. Right? If I put row is equal to P1 row 1 plus P2 row 2, you can check that this will be equal to P1 comes here because it's just a constant, row 1 plus P2 row 2, and then this is a map of row 2, this is a map of row 1. ठीक है मनी? Linearity, अगर ये रो की जगह पे हम P1 row 1 plus P2 row 2 पुट कर दें, can you see the linearity satisfied? ठीक है ना, क्योंकि ये दोनों पे डिवाइड हो जाएगा. अब्बास, कैन यू प्रूव इट? है मे बी, लेट्स चलें कर देते हैं. सो इसके यहाँ पे रखें ई रो, मैं इसके ऊपर रख देता हूं ई आई P1 रो 1 P2 रो 2 ई आई डैगर. तो ये आ जाएगा मैप ऑफ रो इज सम आई ई आई P1 बाहर निकाल लेते हैं, रो 1 ई आई डैगर, इधर भी P2 बाहर निकल जाएगा, ई आई रो 2 ई आई डैगर. सो this is just a map applied to state row 1, and this is just a map applied to state row 2. We see that this is linear. Let's check the complete positivity, and this is a little bit trickier. So suppose that our principal system is divided into two parts, RQ. Okay, so this is our cell principal system. It's not system environment, it is our system. Let's say it has two parts, R and Q. And suppose we have some giant state of this system, we call it psi, and the output phi I is obtained, suppose, by doing nothing to part of the system and applying this operator EI to the part of the system only in Q. Okay, so let's say I get some state phi I out. So we can see that for any positive operator A, phi I A phi I is going to be positive. Okay, because this is a quantum state. So if I apply this operator, So this is an operator, and this is if this A is positive operator, then this quantum state, when you sandwich it in phi i's, we should get a positive number, because that's the sort of definition of positive operators. So this operator can be density operator as well. Density operator, any operator on the Hilbert space. Now from this we see that if I have state psi of the system, and I apply identity to the R part and my map to only this Q part, and after applying this operator A to this psi and then find its expectation value, this is what I should get. Okay, so operator A applied to state psi, and then this channel applied to this. So we see that we get sum over I psi IR EI and A, and like that. So this is symbolically what I meant over there, that I'm applying my map such that EI only applies to Q and identity to IR. So this is some positive operator. So it means that it is sandwiched between these two, and we can now see that this should be, so this is that, you know, phi I state. This is this. So this is phi I state, and since this is a positive operator, so each of this number is positive. So it means this sum is also going to be positive. So if we write in operator sum form, because of the, you know, positivity of the density operator for any state, it's going to be positive for the sum of the states as well. And here we see that we are applying our operation only on the part of the system and not on the total system. So it means if you are able to express your quantum channel as in an operator sum form, it is physical. That's what actually we mean. It's physical because it satisfies the three axioms. And that's what we are going to be working with now when we do discuss a few channels. So let me now take a couple of examples of channels. And hopefully you'll be able to see the importance of this formalism in modeling several noisy quantum processes. G? Mm-hmm.
बेसिकली मैं डेंसिटी ऑपरेटर को तो डेफिनेशन है नहीं, तो ये है ना कि मैं डिफरेंट प्रोजेक्शन ऑपरेटर
नहीं, वो प्रॉपर्टीज अभी प्रोबेबिलिटीज तो सेम नहीं, ये प्रोबेबिलिटीज मैप की सेम है, ये इनके अंदर चेंजेस आएंगे यहाँ पे। लेकिन देखें ये जो रिक्वायरमेंट है, दिस फिजिकली हैज टू बी देयर। आप क्योंकि दिस इज सिंपल थिंग। फर्ज करें आपने यहाँ पे 10 क्यूबिट भेजी है एक एक करके, 3 जो है वो रो 1 स्टेट में है और जो 7 है वो रो 2 स्टेट में, समझ गए। और अगर आप सिर्फ रो 1 भेजते हैं और ये सिस्टम जो है ये उसको कुछ यूं करता है, और अगर रो जाती है तो ये सिस्टम उसको कुछ यूं करता है। तो अब अगर आपने 10 क्यूबिट्स यहां से भेजी हैं, 3 क्यूबिट्स रो 1 स्टेट में है, 7 क्यूबिट्स रो 2 स्टेट में है, तो आउटपुट पे हमें क्या मिलेगा? 3 क्यूबिट्स इस फॉर्म में और 7 क्यूबिट्स इस फॉर्म में। ऐसे तो यही ये कह रहे हैं। हाँ, अब दूसरा, अब आपका जो प्रॉपर्टीज वाला सवाल है, अगर ये सिंगल स्टेट भी आ रही है रो वन, तो प्रोबेबिलिटीज उसके अंदर भी चेंज होंगी. वी हैवंट टेकन एन एग्जांपल वेयर यू एक्सप्लिसिटली सी, बट देयर इज नथिंग that says that probabilities of this row one are preserved. ठीक है, and we'll see in a couple of examples. All right, अगर clear ना हो तो फिर we'll talk more about it, right? Let's take an example. Let's talk about the phase flip channel. अब ये फेज फ्लिप चैनल जो है, ये किस क्वांटम प्रोसेस को मॉडल करता है? ये मॉडल करता है, अगर फर्ज करें आपका कोई क्वांटम सिस्टम है, सपोज कोई एटम है, आप किसी एक्साइटेड ग्राउंड स्टेट में या कोई कॉम्बिनेशन में है, एंड इट्स प्लेस समवेयर, सो photons are coming and just very lightly scattering off. They're not tuning any, giving any, each photon is not producing any excitation, क्योंकि एनर्जी जरूरी नहीं कि बराबर है जो गैप है 0 1 के. But this scattering process usually induces phases in the system. And let's say अगर आपका ग्राउंड में है या वन स्टेट में है, depending on this, it might be giving it off different phases. So that type of quantum process where you have a sort of a heavy particle means uske jo energy gap hai, it's too much than these photons which are bouncing off, and then the environment is just scattering off of this atom. So hum isko thoda detail mein dekhenge, where we will see that actually the states of environment are changing depending on the system being in either 0 or 1 state or a combination, but nothing directly happening to the system, but it's introducing some phases into the system. Iska jo extreme case hai, it's what we call a phase flip channel, where the phase is flipped depending on कि अगर आपका system 0 state में है, nothing happens, और अगर 1 state में है तो it gets a phase. So I can specify it with this operator formalism. Let's say my one operator is that I have E1 like this, and my E2 is this operator. तो ये जो phase flip channel है, इसका मतलब है कि if I have a state rho and I apply this channel to this becomes E1 rho, E1 dagger plus E2 rho, E2 dagger. अब ये E1 यहाँ पे मैं रखूंगा तो ये आइडेंटिटी है, इसका डैगर भी वही है, सो 1/√2 1 इज हाफ रो प्लस ये आ गया हाफ Z रो सेट. और ये जो Z है हमें पता है कि ये क्या करता है. जस्ट टू रिकॉल, द Z is this operator. If it is applies to 0 state, get it at it is, and if we apply it to 1 state, we get with a minus sign. So ये ऐसा चैनल है कि with probability half it does nothing. कि जो आपकी इनपुट स्टेट है रॉ, वो आउटपुट में वैसे ही चली जाती. बट विद प्रोबेबिलिटी हाफ you get a phase if your system is in excited state, and again nothing happens if your system is in ground state. ये z rho z जो है, that's what it means. Understand कि physically क्या हो रहा है? ये थोड़ा सा extreme case है. We will see कि we can make it more general later on. That if I just put a p here and 1 minus p here, okay, with probability p nothing happens, with probability 1 minus p phase flip happens. But for a moment let's be content with this special case of phase flip channel. अब एक चीज जो मैं ये शो करना चाहता हूं वो ये है कि this phase flip channel is actually equivalent to another channel, because if I define एंड बाय द वे यू कैन चेक, और ये आपने हमेशा करना है कि ये जो E1 E2 है दे satisfy the completeness relation, that if I multiply this E1 with its dagger, multiply E2 with its dagger, and then add both of them, I should get identity. और चूंकि z स्क्वायर आइडेंटिटी होता है तो z को z स्क्वायर से करूंगा तो आइडेंटिटी आ जाएगा, ये भी आइडेंटिटी, ये हाफ हो जाएगा, हाफ प्लस हाफ इज 1, सो इट डज सेटिस्फाई दी कंप्लीटनेस कंडीशन। क्योंकि अब हम इस बिजनेस में आ गए हैं कि वी आर ट्राइंग टू स्पेसिफाई द सिस्टम विदाउट स्पेसिफाइंग द एनवायरनमेंट, तो देन ईच टाइम वी हैव टू मेक श्योर कि at least one thing that our process is complete. That's the only check actually. You can come up with any E1, E2, E3, E4, etc. you want. All you have to do is make sure it's a complete set. Then that will, correspond to some physical process. Doesn't matter कि आप उसको सोच सकते हैं कि नहीं सोच सकते. Okay, but unfortunately, this description is not complete. This is not unique, because if I define my F1 as this projection operator and F2 as this projection operator, I can easily see that I can get this F1 by simply adding these two and divide them by square root 2, and I can get this one E1 minus E2 by 2, right? क्योंकि आइडेंटिटी जो है this is 1 0 0 1 और जो Z है it's 1 0 0 minus 1. So if I add them, this goes away, and this is a projection operator 0 0 वो normalize कर लिया, and if I subtract them, this goes away, this is a projection operator 1 1. But more than that, if I find out this map, let me call it F row, which is F1 row, F1 dagger, and this is complete. If I F1 square plus F2 square is identity. F2 row, F2 dagger. ये F1 की जगह पे ये रख दें, 1/2 कॉमन ले लें, तो ये आ जाएगा E1 plus E2 row, E1 plus E2 dagger plus E1 minus E2 row, E1 plus E2 dagger. और इसको एक्सपेंड करें तो वो जो डिफरेंट टर्म्स है वो कैंसिल हो जाती हैं, एंड यू गेट E1 row, E1 dagger plus E2 row, E2 dagger, which is the same map as this one. So the same channel, same quantum process is being described by two operator sums. You can either choose E1, E2, and then you have this physical sort of significance, or you can choose your operator to this one, and they have a completely different physical, interpretation. This essentially, I'm measuring my system in 0 and 1 basis and forgetting that I measured. So the same quantum process can lead to different description using operator sum, or different operator sum descriptions can actually define the same physical process. And in general, you can show it. I'm not going to show it. It's very trivial actually. And the relation actually is this, that Fi's are related to Ei's unitarily. Let's say Ej, Uij, sum over J, where this Uij, this form the unitary matrix. You can take any unitary matrix और उसके जो elements हैं उनकी मदद से you can start with any set of E operators. You can construct a new set of F operators like this. जिससे मैंने यहाँ पे किया. So this, corresponds to the unitary operator. ये 1/√2 है, ये 1/√2 है, 1 over square root 2 minus 1 over square root. So with this unitary operator, I was able to construct F1 and F2. So in general, we can relate, you can choose another unitary operator, okay? Or uske coefficients की वजह से you can define two and other F1, F2, and they will also be equivalent to this E1, E2. Okay. Finally, I'm done with the basic theory that I want to discuss for this operator and ready to discuss a few examples of these quantum of processes. And for the examples, let me actually start with Zishan's question that's bothering him for a while. Okay, let's see the quantum operations in action. और उसके लिए let's start with this phase flip channel. Okay, so this I'll call it special phase flip channel. Okay, I'll later on define more general phase flip channels. So let's see if I have a state rho, and I know that I can define a state rho like this on a block sphere, right? X, Y, Z, where more specifically, this is Rx, X, Ry, Y, Rc. So ये जो Rx, Ry, Rz हैं, ये तीन real numbers हैं, जिनकी मदद से I can describe the state on this block ball. अगर Rx square, Ry square plus Rz square 1 है, so it means it's a pure state lying right on the surface, but this Rx, Ry, Rz can be less than 1, so that the state could be somewhere inside. But this is a general single qubit state. And by the way, ये जो Rx, Ry, Rz हैं, अगर आपको जनरल स्टेट गिवन हो और आपने ये कोएफिशिएंट फाइंड करने हो, तो इट्स वेरी easy. You can take, let's say, rho and multiply it with x operator and find its trace. This is Rx. You can check over here as well. क्योंकि अगर मैं इसको x से मल्टीप्लाई करूं तो ये स्टेट क्या बनेगी? x, ये तो स्केलर नंबर है, x स्क्वायर, x y, x z. तो remember, x square, y square, z square, they are identities, and trace of identities is equal to 2 for a single qubit case. Or you can check actually a trace of xz and trace of zy and trace of zx, zy, and xy. This is actually 0. All these three products are traceless. So if I multiply this with x, this is x square, this is xy, this is xz. इसका भी trace 0 है, इसका भी trace 0 है, और x का भी trace 0 है. ये x, y, z तीनों traceless matrices हैं. ठीक है ना? क्योंकि x है 0, 1, 0, 1, 1, 0, so traceless. Y है 0, minus iota, iota 0, traceless. और z है 1, 0, 0, minus 1, 1 minus 1 is 0. So this is Rx. Similarly, trace of rho y is Ry, and trace of rho z is Rc. All right. So let's pass this state rho through the special phase flip channel. And see what happens. So the output state, a rho prime, is going to be we can actually let's use this description IZ, because this would be a little bit easier. So I first apply half I plus, then I apply the Z operator half Z rho C. So this is my output state. ठीक है जिशान? मुनीब? ठीक है ना? ये वो मैंने ऑपरेटर जो है वो लिख दिए. अब ये जो रो है, इसको लाके यहाँ पे सब्स्टिट्यूट कर देते हैं। तो ये तो वैसी रो आ गई हाफ आई प्लस आर एक्स एक्स आर वाई वाई आर जी जी प्लस ये जो जी जी है ना इस पे अप्लाई करना है। तो एक जी इधर से आ रहा है, एक जी इधर से आ रहा है, ये हाफ मैंने लिख लिया। अच्छा एक हाफ ये है रो का और एक हाफ इधर है, तो ये बन गया 1/4। तो ये आ गया जेड स्क्वेयर। दूसरी टर्म आ जाएगी आर एक्स जेड एक्स जेड। तीसरी टर्म आ जाएगी आर वाई जेड वाई जेड आर जी जेड स्क्वायर जेड। ये आ गया हमारे पास। ओके सो ये बन जाएगा हाफ आई प्लस आर एक्स। अच्छा ये भी मैंने गलत तो नहीं कर दिया, ये रो के साथ भी एक हाफ था, एक हाफ इधर है, तो ये भी 1/4 है। आई प्लस आर एक्स एक्स आर वाई वाई आर सी सी। अब ये मैंने देखना है कि स्टेट को क्या हो रहा है, तो आई थिंक द बेस्ट वे इज टू जस्ट फाइंड आउट द न्यू आर एक्स आर वाई आर सी and relate them with the previous Rx, Ry, Rc. Then I'll be able to see if I have a general state here, what happens to it, where the new Rx, Ry, Rc goes. तो ये आ गया। अच्छा इस इधर देखें तो ये बन जाएगा 1/4। दिस इज जेड स्क्वायर आइडेंटिटी। अब ये है जेड एक्स जेड। तो let me just keep it as it is. I can simplify it again, but I think it's better if I just leave it like this. Z y z plus r z. ये z square identity होगा, so this is z. Now let's see what this z x z is, and क्योंकि मैंने फाइंड करना है let's say r x, तो इसको मैंने r x से x से मल्टीप्लाई करके, तो बल्कि let's actually do so r x prime is trace of x rho prime ट्रेस ऑफ इस सारे को x से मल्टीप्लाई कर देते हैं। तो ये 1/4 इधर भी कॉमन इधर भी कॉमन है, ये मैं बाहर ले लेता हूं। इधर x मल्टीप्लाई किया, ये x स्क्वायर हो गया, ये y x हो गया, ये z x हो गया, ये 1/4 बाहर जा चुका है, ये i x हो गया, ये भी x हो गया, ये है x इधर लेफ्ट से लिख लेते हैं x z स्क्वायर, क्योंकि ये भी x z है, प्लस r y x z y z प्लस r z x z। ओके सो x का ट्रेस भी 0 है, इस x का ट्रेस भी 0 है, ये x स्क्वायर जो है ये आइडेंटिटी है, तो इसका ट्रेस 2 होगा, तो ये आ जाएगा 2rx। ये yx है, इसका ट्रेस भी 0 है, zx का ट्रेस भी 0 है, और ये x है, इसका ट्रेस भी 0 है। तो बाकी क्वांटिटीज रह गई हैं, ये rx x z स्क्वायर एंड ry x z y z। ये आ गया। अब हम इनका ट्रेस कंप्यूट कर लेते हैं। उसके लिए let me start here. So I have, let's first compute xz. x है 0 1 1 0, z है 1 0 0 minus 1, 0 1 1 0 is 0, 0 1 minus 1 1 0 1 1 0 0। ये आ गया xz, ठीक है। और इसलिए मैं देखें वहां पे xz का ट्रेस 0 लिखा हुआ क्योंकि सब ट्रेसलेस, लेकिन मुझे xz स्क्वायर चाहिए, तो xz स्क्वायर के लिए इसको मैंने इसी से मल्टीप्लाई करना 0 -1 1 0 से। तो अब ये बन जाएगा 0 -1 -1 0 0 0 0 -1 0 या माइनस। सो इसका ट्रेस आ जाएगा -2। ओके ट्रेस xz स्क्वायर। अभी हमें वहां पे yz एक्स जेड वाई जेड का भी चाहिए। तो ये तो एक्स जेड तो मेरे पास तो ये आ गया, तो वाई जेड मुझे कंप्यूट करना पड़ेगा। वाई जेड क्या होगा, y है 0 माइनस आयोटा, आयोटा 0, z है 0 नहीं 1 0 0 माइनस 1, तो x z आ जाएगा 0 आयोटा आयोटा 0। ये आ गया x, ये है y z। तो अब जो x z y z है वो देख लेते हैं। x z y z, ये x z है 0 माइनस 1 1 0, ये y z है 0 आयोटा आयोटा 0 0 माइनस आयोटा 0 0 0 0 आयोटा और 0। तो इसका ट्रेस आ गया 0। तो इसका मतलब है कि आर एक्स प्राइम अब मेरे पास आ गया, इसका ट्रेस -2 है, राइट। ये ट्रेस यहां पे आना चाहिए था, क्योंकि ये मैंने ट्रेस ले लिया हुआ है, और इसका भी ट्रेस। तो इसका ट्रेस 0 हो गया, इसका -2 आ गया। तो आई गेट नाउ, ये आर एक्स कॉमन ले लेते हैं बाहर, 2 भी कॉमन आ गया, 4 यहाँ पे आ गया 1 माइनस 1 0। ठीक है जिशान, गड़बड़ तो नहीं हुई? एक चीज आप देख लें, स्टार्टिंग स्टेट का आर एक्स जो मर्जी है, चैनल से गुजरने के बाद स्टेट का आर एक्स प्राइम 0 हो गया। मिक्स तो डेफिनेटली होगी, अगर ये स्टार्टिंग में मिक्स नहीं भी थी, ये स्टार्टिंग में भी मिक्स हो सकती है। आर एक्स माइट नॉट बी 1, लेकिन अगर स्टार्टिंग में मिक्स हो या ना हो, एट द एंड वी हैव अ 0। ओके, सिमिलरली इसका जो आर वाई प्राइम है ना, वो आप फाइंड कर लें, एंड यू नो हाउ टू डू इट। मल्टीप्लाई दिस स्टेट विद वाई, एंड एक्चुअली आई थिंक ये भी 0 आ जाता है, और जो आर जी प्राइम है इट रिमेन्स अनचेंज्ड। सो दिस इज अ चैनल दैट मैप्स द ब्लॉक स्फीयर। अगर आप ब्लॉक स्फीयर से स्टार्ट करें तो यू गो टू अ नीडल अलोंग z एक्सिस। ठीक है, z एक्स के जो भी स्टेट यहां कहीं पे भी है, एट द एंड द स्टेट इज आइदर 1 और 0, or actually it's not 1 0, it's going to be, I think, a maximally mixed state of 1 and 0 state, but it's going to be along z axis, no x and y component. All right, any question? अच्छा, अब ये जो फॉर्मलिज्म है, इसका एक ड्रॉबैक है, एंड आई होप कि आप में से कुछ लोगों ने इसको नोट किया होगा, और वो ये कि वी आर नाउ वेरी फार रिमूव्ड फ्रॉम द एक्चुअल फिजिकल प्रोसेस। We say, okay, these are our operator E1, E2, and we see what happens to the input state. This might or might not, represent some process that we can picture very easily. But that's actually the business of working with noisy quantum systems. You have an environment. Suppose you have your atom somewhere, and the environment is doing something to your system, to your atom. And unfortunately, we can't completely specify the interaction between the system and the environment. And that's usually the game. But in most of the time, we can approximate what is happening by what is being done by the environment to the system approximately. And this is one approximation. Now, आप कह सकते हैं कि मेरा एटम जो है वो हो सकता है मैंने 0 केल्विन पे उसको रखा हुआ एनवायरनमेंट. Suppose in at least in a thought experiment, it's possible that your atom is in at 0 Kelvin and your vacuum is a classical vacuum. There are no fluctuations going on. So there's nothing that is disturbing your system. then of course nothing is happening to your system. Rho goes to rho. Your map should not do anything to your system. By the way, this is also a trouble. We call those maps unital maps that take identity to identity. But anyway, so that's a separate thing. अब एक एटम है वो 5 केल्विन पे है, यानी कि आपने कहीं पे रखा है एनवायरनमेंट 5 केल्विन का. अब एक एटम जो है वो 300 केल्विन पे है. अगर दोनों का सेम भी फिजिकल प्रोसेस हो के there's nothing close by and only microwave background radiations are scattering off and the environment radiation, even then, और अगर आप इसको as a scattering process भी मॉडल करें, then you can say कि even E2 in this form may not completely specify the physical situation. You might want to have sort of a general phase flip channel that you say, okay, your E1 is P, or let me specify with 1 minus P. With 1 minus P over square root 2, it's an identity. And your E2 is P square root 2 Z. In this case, your map can be read as E1 rho E2. Okay, let me even take this 2 away. So then this would be 1 minus P rho plus P Z rho C. So now this is a little bit general phase flip channel that says that with probability P, suppose P is 1%, 0.01. So with probability P, your system is having a phase flip. And with probability 1 minus P, that 99% of the time, nothing is happening to your system. So by tuning this P, you can sort of understand the impact of different, let's say, temperature or different things on what is happening to the system. This अब इसको आपने एनालाइज करना है exactly the same चीज है, बस P एक पैरामीटर आ जाएगा, and we'll actually do it in the next class. I'll try to solve this phase flip channel in general क्योंकि ये काफी important channel है. It mimics what is called the phase damping of quantum systems. कि अगर आप quantum systems जो कहीं पे even कहीं रखा हुआ है, it's interacting with a noisy environment, with the passage of time, even if you prepare your system in a pure quantum state, suppose आपने excite करके pure 1 state में कर दिया या 0 state में है या कोई superposition state है, pure quantum state. So after a while, due to scattering by the environment, it dephases completely and becomes a random mixture, classical random mixture of 0 and 1 states, without inducing any transition into the system. जो transition system है उनके लिए भी हम will study some model. Okay, so this is a sort of a way to generalize it. ठीक है? As a practice, let's do one channel जो आप लोग अभी करें. It's called a bit flip channel, and I'll give you a special bit flip channel or general bit flip channel I will solve in the next class. So this special bit flip channel is nothing happening to the system with half probability, and its bits being flipped with a half probability by x. ठीक है, ये ऐसा system है कि with probability, this means that channel is specified like this: rho plus x rho x. और फिजिकली इसका मतलब है कि आपका जो सिस्टम है 50% चांस है, in a given time interval, nothing happens to it, it stays the same. But there's a 50% chance that the bit is flipped. अगर आप 0 में है, you go to 1, और अगर 1 में है, you go to 0. This is called a sort of a bit flip channel, and it models the situation कि जहां पे जो आपका system है, it's placed in a bath of photons, let's say, which have the same energy as equal to this, gap. So it can, induce transition this way, or maybe not do anything, or the other way around as well. So this type of physical situation can be modeled by this bit flip channel. Of course, इसमें भी I can introduce probability depending on the density of the photon, photons around in this environment. क्योंकि कुछ environment might contain, a lot of photons. Some environment can contain fewer photons. So you can model that thing by tuning the probability. But for this quiz, let's work out what would happen to rho. So I want you to find me Rx prime, Ry prime, and Rc prime as a function of Rx, Ry, Rc. Just do it like that. आपको वो formula भी कुछ helpful होंगे. हाँ हाँ भी
क्लास का टाइम लिखना.
अच्छा, हमने फैसला नहीं किया था कि कुछ टाइम जो है वो एक्चुअल लिया करेंगे. आप लोगों को जाना है? मैं इस तरह से सिर्फ एक ही करते हैं. लेट्स वर्क आउट. तो फिर जो दो हैं, आई वांट दिस चैनल इन होमवर्क सो यू कैन वर्क. Shouldn't take more than 2 minutes. I don't know. आप एक तो घबरा जाते हैं बड़ी. अच्छा, मैंने आप लोगों के मीटर चेक किए हैं, तो आई एम रियली डिसअपॉइंटेड टू से द लीस्ट. तो मेरा ख्याल था आप में से काफी लोगों ने डेंसिटी ऑपरेटर्स पहले भी पढ़े हुए हैं, तो लेकिन वहां से मुझे लगा कि आप लोगों को डेंसिटी ऑपरेटर्स की अभी भी ऑलमोस्ट